Welcome to Empowered Learning. This video will be about how to use definite integrals to be able to study and calculate the moment of a particular object, as well as the center of mass, also called a centroid, being able to locate that particular point on a particular object or figure as well. So in many situations, structures and mechanical systems that are studied by engineers as well as physicists tend to behave as if their entire mass were concentrated at a single point. Another way of putting that is what we could do is we could take an object or system and we could reconfigure it or translate it as being just this figure acting at this one particular point. Okay. And so we know that in doing that, all the action that's going on for that object or figure will be at that center of mass, or sometimes it's called a centroid. Now, some things that we could possibly model like this, I've listed here. I'm going to read them off so that you kind of get an idea of the many things that we could use moments in center of mass for. Okay. So first thing, planet revolving around its sun. Okay. If we had a wrench or a rod, and let's say we let it go, and as it drops to the ground, it's going to rotate as it falls to the ground. Okay. We could have two people trying to balance themselves on a seesaw. We could balance a plate on, let's say if you're trying to balance a plate on your finger, or if you're trying to balance a thin rod of a sharp object. Okay, so on a sharp object, I should say. So let's say if we're trying to take a rod and we want to balance it on our finger, or if we want to balance it on a knife, something like that. So all those situations and similar ones all have this one thing in common, and is that their center of mass of each of the objects in these situations affects its behavior. Okay. So for instance, a planet revolving around its sun acts just as a mass at a single point revolving around another mass. Okay. And in this case, if the Earth is the original mass, then it means the sun that we know it would be the other mass. Okay. Now, a wrench or a rod, like I said before, if we were to have it and then let it go and see it fall to the ground, if we looked at it fall in slow motion, we would see that that wrench or rod, even though it's falling vertically to the ground, is actually rotating, and is actually rotating about its center of mass. Okay. The position of seesaw stops moving when two people are on either side of the seesaw could be replicated if both people could stand on the seesaw at some displacement value x from the center of the seesaw. Meaning that if we could have, and I say both people, it could really be one. If there was one person actually standing somewhere on the seesaw to the left or to the right of where the center is, depending upon the makeup of the seesaw, you would see that the seesaw would be horizontal. Okay. Now, in the case of the plate, the location of where a plate or thin rod could be balanced on a finger or other sharp edge or object is exactly the place where the center of mass of that particular object would be. Okay. So what we're going to go over in this particular video is to, first of all, study what moments are and see how that all plays a role into calculating the center of mass or centroid for an object. And we're going to do it in very specific type situations here. And so the first thing that we'll look at is a one-dimensional case where we're looking at a thin rod, wire, or strip of something. Okay. The next thing that we'll do is we'll have a thin plate covering some region. So in other words, this will be our two-dimensional figure, and we're going to figure out what is a moment in those, or what are moments in those situations, as well as how to use those moments to be able to calculate our centroid or center of mass in that situation as well. Okay. And in the two-dimensional case, we're going to look at a case where we can model the way that this thin plate is going to look on the surface. Is going to be by it's going to be a function that's going to model either the top or the bottom of the plate, and the other side of the plate, either top or bottom, will be the x-axis. Other times we will define the top and bottom of the plate by two different functions. And so in that sense, of course, we'll have to consider the difference of those two functions in some instance. All right, so we are first going to talk about our one-dimensional case where we are trying to find the center of mass of some thin rod, wire, or strip. So what we want to do here is consider figure A, and notice that figure A is going to be our representation of a thin rod, wire, or strip, and we have three different masses that are on this particular rod or strip, okay? And so the object here is that we want, with those three masses being on this rod, what we want to do is balance this rod. And notice that what we're balancing it on is going to be some kind of support device. Of course, the formal word for that is fulcrum, but it's essentially just a support device. And we need to find out, how much does mass 1 and 2 need to be? How much does mass 3 need to be in order to balance this particular thin rod, wire, or strip? Okay. So one of the things that we know here is that, just kind of using common sense, is that we know that these masses here, if we're in an environment where we have to consider gravity, then each of these masses will have a corresponding weight to it, okay? And of course, that weight will just be whatever the mass is times whatever gravity is going to be. And so my point here is that we know that it's going to act downward. So we're going to have the weight of this mass and the weight of that mass going downward. We're going to have the weight of this mass going down. Now, in this sense, we know that just looking at the masses 1 and 2, if the mass is going down, we know that these two masses here are going to make our thin rod spin this way, okay? In other words, where it's going to try to rotate counterclockwise, okay? Now, mass number 3 over here has a corresponding weight, and since it's going down, it's going to try to make the mass actually go this way, okay? In other words, rotate clockwise, okay? Now, notice that both of these masses, M1 and M2, have their corresponding weights, and because of that, it's making the rod try to rotate one way. Mass 3 has its corresponding weight, it's trying to make the mass rotate in the other direction. And what we want to do is balance out the tendency for this rod to rotate in either direction to where it doesn't rotate at all, okay? Now, this tendency for the rod to rotate, whether it's going to rotate in a counterclockwise motion, like what we see here, or if it's going to rotate in a clockwise motion, like what we see here, this turning phenomenon here is called torque, okay? And so what we're going to do here to try to come up with a way to figure out the moment and then after that, the center of mass location for this particular rod that we are looking at, we are going to have to balance out all those torques that are going on, okay? So in other words, the torque that's making the rod spin counterclockwise, and balance it out with the torque that's trying to make the rod spin clockwise. And note here that we are interpreting torque as being positive whenever it spins in a counterclockwise motion. And we are interpreting torque as negative when it spins in a clockwise motion, okay? All right, so let's go ahead and move forward here and see how we're actually going to, from a math standpoint, figure out the total torque of the system, and from that, try to get to the center of mass. All right, so here we're looking at the different torques that are being applied based upon the mass, and I'm just calling that T sub I here. Again, if I go in a counterclockwise motion, my torque is considered positive. If I go in a clockwise motion, for torque is considered negative. So the tendency for the total system, in this case, the rod that we're talking about, to rotate about the origin is the sum of all the torques, which I've talked about before. And so the sum of all these, if we wanted this to balance out, of course, the sum of all of this is going to have to equal 0. Okay. So in general, this is what we would say here. Total torque is just going to be the sum of all the masses that are on the particular rod. And I'm just looking at it if I had n number of masses here. Now, the point I want to illuminate here is that for each one of these masses, it has this corresponding weight to it. And thus, we know that we could factor out this common factor of gravity out of everything. And so with that, we know that gravity is just acting as a constant, and we can concentrate on this part here. Okay. Now, that quantity of the summation of the product of the mass and how far it is from the origin, or how far it is from the fulcrum, or where you're trying to balance it, is a part of torque of the system that is characteristic to the system itself. So in other words, it's an intrinsic part of the system. And it doesn't matter whether I have gravity applied, gravity not applied, whether I have environment on Mars, environment in Pluto, environment in space. This product of the mass times how far it is from the origin, or where you're trying to balance everything at, and summing all that part is going to be characteristic of the system no matter what. And of course, what we call that is the moment of the system. So the moment is the intrinsic part of the system that doesn't change regardless of what environment that particular thin rod is in. Okay. So in noting this, since gravity is really not a factor, what we really want to do is not necessarily balance the torques so much to say. What we want to do is balance the moments. Okay. So the moment of each mass and how it's going to interact with the rod, that's really what we want to balance here. So now, knowing that we really just want to deal with the moments here, what we want to know now is what point, and since this is one-dimensional, we're just talking about an x value, and we're going to call this x value x bar. So what one-dimensional point x bar on our system, in this case, the system is our rod, but our rod is looking like the x-axis here. We want to know what point on that x-axis of rod could we locate a place, locate the total mass, and of course that's going to be the sum of all the masses of the system to produce the same torque, so that our system would be balanced. That is to say, have no tendency to rotate. Okay. So I'll read that again just to make sure that it's clear. So what point x bar on our system could we locate the total mass of the system to produce the same torque so that our system would be balanced? In other words, here, mathematically speaking, I want to know, if I look at all the torques that I'm considering here, the sum of them all, then I want to know, if I'm looking at this in terms of torque, what single x value can I have for all those masses here, such that if I had it at this X value, it would balance out all the torques that's being applied from the mass because of gravity acting on the particular mass on both sides of it. Okay. And so we see here that if we were to actually fill in everything, of course, we know torque is just going to be the let's see, the moment here. Let me erase that. So it's basically going to be the moment times gravity. And that part is the moment times gravity. Or you can look at it as torque is going to be the weight, sum of the weight of all the objects, times how far each particular object is from the place where you're trying to center everything. Okay. And of course, on the right side here, you just have the sum of all the weights of the corresponding masses times some X value, to where if we pick the right one, everything is balanced out. So mathematically speaking here, if we were to take the right side of this equation, subtract it to both sides, and then factor out the G's here, then which stands for gravity, we would have that. Of course, divide both sides by G. And of course, this would just reduce to 1. And if we take that and then add this back onto the other side, then we just have the situation here. Okay. And so because of that, the thing that we want to find is this X bar. So we could take this quantity here and divide it by this quantity here, and we would have what we need. And so we see here that the numerator of this is called the system moment, which means is the sum of the moment of each mass. And of course, a moment is defined as the mass times how far it is from the place where you're trying to balance everything. And so for simplicity's sake, we're just going to say that X of I is just going to be how far the mass is from the origin. Okay. And ideally, we would want to have this rod or a wire balanced at the origin, but that's not going to always be the case. So I'm not going to use that language anymore from this point for that reason. Okay. Now, of course, the summation of all the M sub i's is just going to be what the system mass is, which is what is the mass of the entire object. Okay. And so if we have masses everywhere on the object, then of course the sum of all those masses together would actually be what the mass of the thin rod or wire would be. Okay. So from here, it turns out that our system will balance when the sum of the torques and this sum of the weights times this X value here equals 0. And of course, the location of X bar is precisely where this system's center of mass is. So for a one-dimensional system, this is essentially how we find its center of mass. We just basically look at the system moment, which is all the masses and where they're located on this one-dimensional figure, figure out how far they are from the origin, multiply those things together, add them up, and then divide that by the sum of all the masses that are a part of the system, and we get what the center of mass will be. Now, of course, the last thing I'll say about this before we move on is that notice that this value X bar is assumed to be a distance from the system's origin or fulcrum. Okay, so that's why I was saying that it's rare that whatever we're calling the origin will actually end up actually being the center of mass location as well. It can be, but usually it's not. All right, so at this point, I know we've gone a little deep in the theory here, so I just want to summarize before we continue on, because we're at a critical point now to where we need to make sure that we understand what we've done in the past versus how we are going to move toward actually coming up with some formula for the center of mass in a way that resembles what we use in calculus. And in particular, I'm talking about us using definite integrals here, okay? So we realize that if we had a one-dimensional system and the system had some a string of masses that are on it, and that's the thing that makes it have the mass that it has, then what we realize here is that it's really the moment or the sum of all the moments on that particular system that's actually controlling when it rotates. Now, of course, we could take the torques, which is just taking the moments and multiplying that times gravity, and include that, but really that's not the important part to it, okay? Since gravity is going to be acting on every object that we look at in the same way. So that's a constant that we don't need. So essentially we want to balance the moments, and of course our moments will either make our one-dimensional system either rotate clockwise or counterclockwise. And we want to add that up and make sure that all equals 0. And we see that in doing that, what we end up having is the quotient of the system moment, which would just be all the m sub i's times the x sub i's added up. And we're going to divide that by the system mass, which is all the m sub i's that we have in the system, okay? So that's where we are. Now, the reason why I'm pausing here is because notice that we don't have this in a form to where we can start talking about calculus yet, okay? And so what we're trying to do is move toward being able to do that. So if we can assume that the distribution of mass throughout the system is continuous, keyword is continuous, we can model our one-dimensional formula for the center of mass with integrals instead of summation signs, okay? And so you got to remember here that when we talk about integrals actually come from saying the limit as n approaches infinity of the infinite sum of something else, okay? And so whatever this stuff is here is what it is. But if we take both that summation and that limit as n approaches infinity, technically speaking, that is what our integral sign is, where our integral sign comes from Cal A. So here we want to see how we're actually going to form this using integrals instead of summation signs. So to do this, we're going to consider this figure B here, and we're going to assume that we're going to take a slice of this one-dimensional figure. And I've just kind of drawn it fat so that you can actually, see what's going on, but we're still assuming that this is like a thin rod wire, okay? So if we cut our thin rod in figure A into small pieces, and we're going to say each piece has a mass of delta m sub I, and we're saying that because of the fact that if this whole rod here is going to be system mass, and we're going to call it, let's say, big M here, then of course, if we could break this up into a bunch of pieces here, this would be the first piece, this would be the second piece, third piece, fourth piece, fifth piece, so on and so forth. And each one of those pieces would have a mass associated to it, and that is what our m sub I would be, okay? So m sub 1 would be the first piece, m sub 2 would be the second piece, m sub 3 would be the third piece, okay? And we know that the change in the mass going from here to here is going to characterize what's going on there, okay? Now, the reason why we are saying the change in mass is because we don't know for this thin rod, we don't know if the mass is uniform throughout the rod or if it's, more mass in some places in the rod than others. So since we don't know that, we have to take into account that it may be possible that the mass is more in some places than the other. So even though it would be great to refer to all these masses just as an m sub I, it's more proper to call it delta m sub I, or change in the mass from one location to another. Okay, so that's one thing here, and I'm going to erase. So now that we can talk about how we actually come up with this formula for the change in mass. So to come up with the actual change in mass, to be able to characterize that, notice here that I have this lowercase delta times delta x sub I. Okay. Now, x sub I is just actually going to be the change in the x values from one location to another. So if I'm looking here, this would actually be the change in the x values from one location to another. That is what delta x sub I would be. X sub I would be, of course, located right in the center of this particular piece of mass for the rod. And that's just to keep everything simple, to put it in the center. And this lowercase delta here, again, is the density. And in a one-dimensional type situation, that is going to be mass per unit length. Okay. Now, when we go to 2 dimensions, we'll be looking at mass per unit area. And if we were considering 3-dimensional cases, then we would do mass per unit volume. Okay. All right, so now that we have that together here, we're going to note a few things. And I'll erase this first before we do it. So number 1, we know that the center of mass, which is this x bar that's right here, so that's what we're calling it, is going to be approximately the same as the center of mass of all the masses, delta m sub I, where I is just some positive integer number, and it's going to go all the way up to n, however much we want that to be. Ideally speaking, we would want n to approach infinity here. But right now we're just keeping it general. Now we know that the moment of each piece is going to be whatever the change in the mass is from left end of that point to the right end of, left end of that piece to the right end of that piece, times how far it is from what we're calling the origin. Okay. We also see that if the density of this particular this piece is going to be, let's say, little delta sub I, and again, I'm calling it that because the density of that rod may be more in some places than it is in the other. So I can't assume that the density is going to be uniform throughout. Okay. If I'm told that, or if I know that, then that's one thing, but I can't assume that just, coming up with this formulas here. So we know here that our delta m sub I is going to approximately equal to this little delta sub I, which is going to be, again, the density per unit length here, times this delta x, which is going to be a length. Okay. And so we know that mass per unit length times length is just going to give us whatever the mass is. Okay. Now, if we look at all 3 of these situations here, then we're going to be able to conclude the following. So number 1, we know that our system moment here, if you remember, we said our system moment was the summation of the product of mass times how far that mass is away from what we call the origin. And since we don't know whether the mass is uniform or not, we're going to call our mass delta m sub I. And of course, that's going to be multiplied times a location that is so far away from where the origin is. So we've changed the way that our system moment looks now. And just going back here, what we originally had was just this, okay? But now we've gotten a little bit more precise and said, all right, well, we can assume that the mass is going to be the same for that piece. So what we're going to do here is just basically call it delta m sub I. And again, we say that because from this particular point to this particular point, the mass of this entire piece could actually change if the mass is not distributed out uniformly throughout the Y, especially for that little piece of it, okay? All right, so we know that our X bar, which is going to be our center of mass, should roughly be about whatever the system moment is divided by the system mass. Of course, our system moment, we just got to describing that. Our delta m sub I is just going to be the little delta sub I times delta x. And then from here, if we're going to have n of these pieces, then we could rewrite everything like how you see here, where we have the summation of the product of x sub I and delta m sub I for the system moment, and we have the summation of delta m sub I for the system mass. And of course, since we're considering n pieces of that particular rod, then we're going to consider that. Now, the basic idea is this. Once we consider our system moment, our system mass being in this form, and of course, we go ahead and substitute in the delta m sub I as just the density times the change in the x values for both the system moment and system mass down here. Our goal is to say, well, for this thin rod, can we increase the number of pieces we break that rod into an infinite amount, theoretically, okay? If we do that, then essentially what this is like now is saying, well, let me do the limit as n approaches infinity on all this information here. But if I do that, that's just like me also saying I want the limit as n approaches infinity for my center of mass, okay? So on the next page here, you see that I have written exactly that. So I have the limit or the behavior of my center of mass as the number of pieces I cut my thin rod into ends up being an infinite amount. Notice here that we got that limit of summation, where that summation there, since n is approaching infinity, this goes to infinity. So we know that we can replace that limit and that summation together with an integral sign, okay? And of course, that's why we see the integral here and we see it here on bottom. We also know that anytime we have anything defined in terms of a change in something like this change in x or delta x, we know that the smallest possible theoretical change in x values would be this differential dx. So that's why you see it there, okay? Of course, this delta sub I, a little delta sub I here, these are the same. However, we're not going to reduce those deltas to 1, because one of the things that we're also going to see is that our density may not always be constant, okay? So sometimes it may be a function of x, sometimes it may be a function of y. So we have to be privy to that and make sure to not just reduce those things to 1 unless we know that our density is going to be uniform throughout the object that we're dealing with, okay? So because of all of that, if we are looking at our rod here and it starts at some value x equals a, and it ends at some value x equals b, then of course we now have our limits of integration that we're going to look at the moment for this particular figure as well as the system mass for this particular figure. Okay, and of course if we take the infinite sum of the system moments and divide it by the infinite sum of the masses as the number of pieces that we cut that rod into approaches infinity, then here we can figure out what our center of mass, or our one-dimensional centroid would be in this case, in terms of integrals, or in this case definite integrals. And so this is how we come up with our formula for figuring out the center of mass for a one-dimensional figure here. And again, you see that the moment, and this is just going to be the system moment, everything is going to be about the x-axis because we're talking one dimension here. If we know what our density is, then, and we know where to start and where to stop, that's pretty much all we need to know. Okay, and same thing for our system mass. Here, if we know what the density of the object that it is that we're dealing with, then we pretty much know everything that there is to know for. Okay. Now, to summarize, we see here that our moment about the origin, and notice here I have this subscript there, x, because of the fact that we're doing this about the x-axis. If we're looking at it like this, or horizontally, I should say, then for that, we see it looks pretty much like what we went over earlier, which is going to be the integral from a to b of x times the density dx. The system mass is just going to be the integral from a to b of the density times delta x. And of course, center of mass is just going to be the quotient of the moment and the mass. Now, of course, if we're looking at everything in terms of the y-axis, which means we're looking at everything vertically, then of course, instead of having x's, we would have y's. And that's pretty much all there is to that. Okay, so to conclude this video, I'm going to go over one example to where we look at a one-dimensional figure, and we're going to figure out the moment about this one-dimensional figure, and of course where the center of mass is going to be as well. So let's go ahead and take a look at it, and then afterwards I will make another video that's going to be part 2 for this, and we're going to talk more in depth about how do we deal with moments with 2 dimensions. And so I spent a lot of time with the theory here for the one-dimensional figure because it's actually going to play a role in helping us to build what we need to know about the 2-dimensional figures and finding the moments and the center of mass for those. And so I won't need to take as long to kind of build up everything for the 2-dimensional ones because of that. And another reason is that I want to spend more time on doing examples for the 2-dimensional figures because that's what you're going to see more of anyway. Okay. All right. So for this example, we have the center of mass of a metal rod with one end at the origin and the other end at x equals 10. So basically this rod is going to be 10 units long, whatever those units are. And we see from right to left, so that the thickness of it from right to left is so that the density of it changes as it goes from right to left. So we have a rod, it's kind of looking like this from x equals 0 to x equals 10. And as we get closer and closer to x equals 10, the density of the rod increases. So that means that essentially it's actually going to weigh more on the x equals 10 side than it is the x equals 0 side. Okay. And it's a gradual increase in density, which means there's a gradual increase in weight as well. Okay. So from here, of course, our main goal is to find this center of mass. Now, since we know that we're looking at a rod and we're looking at it horizontally speaking here, we could look at it vertically, but to make life simple, we're just going to look at it horizontally. We know here that this is going to be the formula for the moment about the x-axis, and we're assuming that this is going to be an x-axis here. And the system mass is just going to be the sum of all the densities from x equals 0 to x equals 10. And notice here that our density is defined as 1 plus 1/10 of x. So you see that it really does make sense for me to keep those little deltas in there because of the fact that it's not constant. Okay. And of course, our center of mass is just going to be the quotient of the system moment divided by the system mass. So first thing we need to do is use our formula for, well, not formula, but our function for the density, describing the density of the rod. And we see here that it's going to be x times whatever this density is. And then from there, we can just multiply the x into both terms. And then from here, this looks like simple first year calculus, where we just take the antiderivative of both terms and use the net change theorem to figure out what our corresponding value would be. And so in looking at that, you see once we're here, we take the antiderivative, clean things up, clean it up a little bit more. And then after that, we plug in 10 everywhere for x, minus plug in 0 everywhere for x. And then we see that we end up getting 250 divided by 3 kilogram meters. Okay. And so next thing that we need to calculate is the actual system mass. And so to do that, we just take our density, which was d of x, which is this 1 plus 1/10 x here. So we just take this and we just integrate that. So again, the antiderivative of 1 is x. Antiderivative of x is x squared over 2. So we have that. Ignore that constant 1/10. And then, of course, from here, we just clean everything up, try to make it look as nice as we can, and then substitute in 10 everywhere, minus substitute in 0 everywhere. And we see that we get 15 kilograms. So once we're done, then of course our moment is just going to be the 250 divided by 3 kilogram meters divided by our system mass, which is 15 kilograms. And of course, those kilogram units reduce to 1, and all we have left is the mass. So that's why once we're done doing all the math here, we see that we roughly get about 5.56 meters. So what that means here is that if we're looking at this rod from x equals 0 to x equals 10, then right around here, which would be x equals 5.56, this would be your center of mass. Okay. And so, of course, what that would mean is, let's say if I wanted to take some kind of supporting device and try to balance it to where the rod won't rotate at all, I would have to balance it right at about x is equal to 5.56 to be able to do that. Okay. And just to be formally correct here, this should be meters. I wrote it there, but I didn't write it here. All right, so this concludes this first example, and it concludes this part 1 of the series of videos. I am going to make another video now for part 2, where we're going to talk about the center of mass of a thin plate covering a region. And this is going to be our way of talking about trying to find the center of mass for 2-dimensional figures. I'll see you in that video.